This is going to be the first video set of notes for CCNA 2, Chapter 1. Somewhat building off of what we did last time. Things have switched around in version 6 of CCNA 2. That we start with routing first, and we move on to switched network second. So we'll be taking a look at some initial router configuration, things we saw last class, how routing decisions are made, and router operation, which will be more of the new material that we'll be seeing in this course. So a lot of this stuff you'll recognize from CCNA 1. Some of it will be a bit new, like familiar things like router initial configuration, things we've already done. These are some things, commands we've already issued already. We've talked about characteristics of a network before, the topology or layout of your network, speed, cost, security implementation, availability, scalability, how easy is it to expand, and reliability of the network. So why routing? Why routing is because you wouldn't be able to communicate with other networks without routers doing their job. You can see that it's going to route traffic between networks, choose a best path, forward traffic to the next router along the path so you can get to your destination. So your router is making those decisions that get you from one network to another efficiently. Okay. We've talked about the internals, the hardware of a router before. They have a CPU, they have an operating system, which is the Cisco IOS, and the devices that we use. Different memory and storage, we've discussed those and where things are stored there, RAM, ROM, NVRAM, flash drive, and potentially a hard drive. So this is all stuff we've kind of seen before, the components of your router, what goes into it. Here's the physical layout of the router. We've also seen this before. You've got your console port, you've got your LAN interfaces, your USB ports. If you're looking to load an iOS or save one to a USB, which is of course different from your console. Console is what we're using to manage. Our WIC slots, if you want to expand, add some serial ports, add some extra Ethernet ports, whatever it is you want to do with your WIC slots. So we've also discussed this, and this is just kind of here for your reference. I do not believe this comes up in testing for CCNA 2 anyway. It will come up in your CCNA general test. More review materials. We've talked about RAM and what's stored there. Your running config, your running iOS, your IP and ARP tables, your packet buffer. You see that all here. Okay. Remember, your startup config is stored in NVRAM, and that then loads into RAM as you boot the router. And so that running config is in your router. That running config is in your RAM. You never have a startup config file in RAM. You never have a running config file in NVRAM. Okay. We also have ROM, read-only memory, that has your boot up instructions, basic diagnostic software. Limited OS in case the router cannot load the full featured OS, which would be in Flash down here. Okay. So it takes you into basically a ROM mode that allows you to recover a device that can't load its OS. Okay, so again, this is review from CCNA 1. Here we've talked about, again, routers interconnecting networks. You've got routers on routers between potentially between you and whichever web server or web page you're accessing, whichever file server you're accessing. So those routers together are interconnecting your network. Each router having multiple interfaces that could be assigned to different networks per interface. Okay, and we'll talk about some other things you can do with those interfaces as we go on through CCNA 2. Routers do choose the best path to make your communication as efficient as possible. You can see in the first bullet point that we have both static and dynamic routes, and you can think of that just like static and dynamic IP addresses. Static are routes you're going to enter yourself manually. Dynamic are going to be learned, well, dynamically or automatically. through some dynamic routing process, whether that be, well, we'll talk about some of them, but you've got OSPF, EIGRP, RIP as dynamic routing protocols that could be used to learn about remote networks. And again, we'll talk about that a bit later. Routers use the routing table to determine the best path to send your packets. There are values that go into that. Okay. Again, that comes up later in the chapter. You've got a metric for distance between your two routers and the most trusted route in the routing table that we'll talk about, which is a value for administrative distance that comes along later. Routers encapsulate the packet and forward it to the interface indicated in the routing table. You've got three packet forwarding methods, basically in order from oldest and slowest to newest and fastest and most efficient. You've got process switching, which would take every packet and it'd be processed by the CPU in this control plane, looking for which interface that packet's supposed to go out and then sending it out that interface on a one-by-one basis. It was very slow, so they improved that to fast switching, which was actually used with process switching if fast switching were to fail or the next hop was not available in cache. So basically what you see here is it would use a fast switching cache to store next hop information. If a packet arrived in the control plane that matched an entry in the fast switching cache, it would just go ahead and send it out the proper interface because it would have a match there. If there was no match in the cache for fast switching, then you'd have to go back to the process switching process, look up what interface it's supposed to go out and go. So this is a way to speed up things a little bit by storing a next hop cache, and if packets matched that next hop cache, then they'd be sent a lot quicker. The flow information is also stored from your packet, so if another packet comes in from the same flow, the CPU won't even be involved in the process for looking at the next hop in the fast switching cache. It'll just be forwarded straight to the fast switching cache and sent out the proper interface. So if you have packets that are all part of the same flow, that speeds things up even more because you don't involve the CPU at all in the process. You're just using this fast switching cache to use the next hop information, to identify the next hop information. If you don't remember what a next hop is, the next hop, remember, is just network to network, router to router. That's your hop. Each router would be considered a hop between your source for a packet and your destination. So in case you didn't remember what a hop was, that's what it is. The last one, the most recent and fastest and preferred Cisco packet forwarding method is Cisco Express Forwarding. So as it says, this is the fastest of the forwarding techniques, and you have this FIB and adjacency table that's responsible for that. The FIB stands for Forwarding Information Base, and basically it contains information for all of the next hops on your network. So basically all the possible destinations for a packet to go eventually, once it learns all that information. Once all that information is learned, then your CPU is taken out of the process. You can just do some reverse lookups in this adjacency table and make decisions there because, well, every next hop basically is mapped, so it makes things a lot quicker. You're not having to make decisions using the CPU, you're just using this table down here. So that's why it's the most efficient of the packet forwarding methods. The forwarding information base basically has, it's like almost like a routing table. It has all of your next hops and all the interfaces that packets might have to go out of without involving the CPU. Here we just have a basic physical topology of how a network might be connected. Simple LAN and WAN connections for a home office, a couple branches here. Basically you just have a bunch of Ethernet setups or wireless setups that connect you to your router or edge router, which would be the router on the edge of your network, which will connect to the internet or to your ISP or the backbone of your network if you are a large corporation through WAN links, typically serial. So it's just a overview of a network, nothing really too new or different there. We've talked about default gateways before. If you want to be able to get off your current network, then you need an IP address, subnet mask, and a default gateway. Your default gateway, again, is the router interface that is connected to your network, the IP address of that interface, actually. And your devices within a network are going to use that IP address to get off the network. And that's about it. When documenting a network, you want to make sure that all of these items are in it: your device names, your interfaces, your IP addresses and subnet masks, default gateways. So if you are documenting your network and how it's set up, that's what you want, okay, at minimum. At minimum. All right. There are other things you could include, but that's what you want at minimum. Again, we have the concept of static versus DHCP. Static being that you assign manually your IP address, subnet mask, default gateway, even DNS server. Dynamically assign your IP address, subnet mask, default gateway, DNS server. So dynamic, automatically. Static, you are manually entering in your information yourself. And we've seen this before, enabling an IP on a host. Static versus dynamic. You do want to know what the lights mean on your Cisco devices. That one blink is 10 megabits per second. 2 blinks for speed, that is. That's this speed indicator up here. 2 blinks for 100 megabits, 3 blinks for 1,000 or gigabit speed on the speed link. Is the link active or inactive? Well, green's active, off is not active, and that's pretty much how it goes for the rest of these. The L here is referring to this L up there. Got the 2 here, 2 there, of course. All right, I do believe you can read, so I will go ahead and proceed. All right, console connections you have available to you. You've got a RJ45 to DB9 if you want to console in through your serial port. Okay, we've gone ahead and looked at those console ports on our devices before. That's again a serial to basically a RJ45, which is a Ethernet head on a port. Okay, you also have a USB port you can use to console in. And you see you can use a USB to serial to connect to that USB type A port. That's the smaller USB port. You can also use just a USB B to A cable, but you also need a driver to make that happen that's available from Cisco.com. The emulation program that you can use to console in PuTTY, TerraTerm, we will be using PuTTY in the class. That's what we have installed on our computers. Enabling IP on a switch. This is not new. We've gone into interface VLAN 1, IP address, yada yada, no shutdown. If you want to manage remotely from outside the network, then you need to have a default gateway in order to make that happen. So we've done this command before. That's review. Again, more review commands, enable password or your privileged exec mode password, your line console 0 password, your line VTY passwords. Done this all before, so I'm just going to skip past that. I'll let you read that on your own. Configuring IPv4 on a router. So we've done this as well. Go into your interface. If you want to give it a description, it's not a bad idea, it's a good idea to give it a description. Can make life easier for you in the future. Give it an IP address, no shutdown, similar to interface VLAN on a switch, but you're using the actual physical interface on a router. Remember, VLAN on a switch is not a physical interface. Oops, wrong way. There we go. IPv6, well, basically what we've discussed is that anytime you want to perform the same process for IPv6 that you did for IPv4, just change the command to say IPv6 rather than just IP, and it should work. Okay, so this is the exact same set of instructions. It's only you're using IPv6 address here rather than IP address. So same instruction set. In IPv6, to enable it on a router, you'll need to, let's see, is that here yet? I don't know. Well, it doesn't look like it's here, but to enable IPv6 on a router, you're going to use the command IPv6 unicast routing. Okay. You are going to, I'm not sure why these commands are not spaced. Because if you try to configure an IPv6 address without having a space between IPv6 and address, then you're going to run into problems. So I'll go ahead and add those in there, why don't I? Also, this should probably be bolded because that's part of the link local creation. Alright, so you type in IPv6 address and the address you want / the prefix at the end. If you want to create an IPv6 address or use an IPv6 address with the EUI process that we've discussed before, you'd type in your IPv6 address, then the address, and at the end you'd type in EUI64 to have EUI generate that interface ID or interface identifier with the EUI process that uses your MAC address. Okay, and then your link local address, remember, if you enable IPv6 on an interface, it's automatically going to have a link local address. In fact, when you enable IPv6 on your router, I'm sorry, just the interface, if you do an IPv6 enable on the interface, it's going to give you a link local address automatically. If you want control over that link local address, maybe you're going to have some logical or incremental IPv6 link local addressing scheme, then you can configure it yourself statically. Otherwise, again, if you enable IPv6 on an interface, it's going to give it a link local address by default. Your loopback address, you may have heard us referring to loopbacks on your end devices on the router. It's similar. It's going to be used for testing, but it is also used for other purposes. It's a way for the router to identify itself in case a link goes down. That could cause problems for you. So your router will use that address as an address to identify the router. In processes such as OSPF, you might have a link go down and that address basically is not valid for the router. The router can refer to itself as this loopback address at all times. It is not associated with a physical port. It is an internal address unique to the router. Okay, so it's basically used for testing and management and a way for the router to identify itself in certain processes such as OSPF. And the command for that is interface loopback, whatever, loopback 0 typically, IP address, then the subnet mask right after that. And it doesn't have to be loopback 0, it could be loopback 1, and we'll discuss the different uses of loopback as we go through the materials, or how it's incorporated, I should say. We've seen these commands before: show IP interface brief. There's an example there, show IP route, which is your routing table. You've got show running config, which does just that. Show interfaces, which is going to show all of your interface information, as well as your packet flow count for all interfaces on the device. And show IP interfaces would be just for showing your IPv4 related information for all interfaces. Okay, so those are our show commands. We've seen them at one time or another in CCNA 1. One more thing on these show commands. There are in the readings some filters that you can apply to these show commands if you want to start at a certain point, exclude some information, include some information. So make sure you take a look at that real quick, at least in the readings. Whoa, I didn't mean to delete that. It's not my intention. Alright, here's your show IP route. Your IPv6 commands, again, just replace IP with IPv6, and you got that. Alright, there's the filter command. So you've got the pipe character after the command. You type in section, include, begin. You can see some examples of that happening down here. You've got the section, it'll show a certain section, brief, include those that are up in the show IP interface brief. Okay. You can see that the interfaces that were administratively down, I know you can't see all that here, up there are excluded when you choose to include up. You've also got, as you can see, a terminal length number you could add in to specify the number of lines to be displayed in your command. Some commands have tons of lines that they will attempt to show you, so you can limit that if you want. You may not need to, because you do have the power to just press enter or spacebar as many times as you want, and then press any other key to stop the device from showing you more commands. So I don't know, maybe that's a better feature or a better use of your time. We've actually worked with this history feature before. How we've used it is when you type in a command and maybe it didn't work correctly, or maybe you just want to repeat a command, you press the up or down arrow key to see the previous commands. By pressing up, if you went too far, you'd press down to move the other direction. That can also be done with Control P or Control N, and that is using the history, command history feature. If you want more commands to be remembered, by default there's only 10 commands. From privileged exec mode, the #, you can do a terminal history size and then type in whatever size you want, and it will store, well, more or less commands depending on what you type in. Here we've got 200, so it would store 200 commands. So there's that. Alright, I think that brings us to the end of this section, not the chapter just yet. Don't get excited. This section is going to go through routing decisions, what happens when your packet arrives at a router and how it makes its decisions as to where it should go next. So the first slide we have here is the switching function, which basically, don't think of switches. It's not a switch layer 2 function. It basically means your router is going to receive a packet and use its switching function to determine or move the packet from one interface to the next. Okay, so you receive the packet through what's called an ingress port, and you send it through an egress port or an exit port. So ingress, incoming, egress, exit, export, whatever you want to call it. Okay, so comes in through this port. The router is going to make a decision based on de-encapsulating everything up to layer 3 and seeing which destination IP address this is headed for. It's going to check that against its routing table, perform a couple processes to make decisions, and then send it out the appropriate interface. Okay, so that's the switching function of receiving the packet, then sending it on back out. As it receives the packet, it's just going to look at this layer 3 information. Okay, it's not going to change it. Layer 3 information doesn't change. IP addresses don't change. But it will change the layer 2 information, because you know that MAC addresses change at every hop. Also, you may need to re-encapsulate the frame to be sent over Ethernet versus sent over a serial link versus sent over, I don't know, wireless or satellite, something like that. So that layer 2 information, the layer 2 frame, does get re-encapsulated and changed. The layer 3 portion is not going to be changed. Okay. You do have MAC addresses down here for each item except for the serial link. MAC information is not necessary for serial links. So that's something to take note of, because it's just a point-to-point connection. There's not any more than 2 devices in that connection, so MAC addresses aren't necessary there. All right, we'll move on. We have talked about how MAC addresses are always going to have a destination of the next hop in your path. So PC1, as it encapsulates the frame, it's going to have a MAC address of R1 that it's going to send to, but a destination IP address of PC2 all the way down here. The IP address does not change, and we've talked about that a bit. Okay, I don't think there's really anything else to talk about on this slide, so you can see you've got a MAC address table, or I'm sorry, an ARP table and a router, MAC address table and a switch. So you got an ARP table and a routing table, and that's what R1's using to make its decision basically here. It has a ARP entry in its ARP cache for not for this guy here, but for the next hop IP. So it sees to get to said network, that network's in its routing table, it has to go to this next hop. Okay, the next hop is R2. So in R1's ARP table for MAC addresses, it has the MAC address for R2, so it has all the information it needs to build that frame and send it back over, or send it along to R2. Because remember, R1's receiving that packet, de-encapsulating it up to layer 3, re-encapsulating a new frame, and sending that along the network to R2. And it's using this information in order to determine where it should be sending that data. Then we have the link between R2 and R3. As stated before, we don't need MAC addresses in a serial link, so that's empty. It's just going to be sent along to the destination of R3 over here without a MAC address entry because, well, that's the only direction it can go. It's the only place it can go. It's a link to point-to-point link. Then at R3, it has a entry to reach PC2. Okay, it's directly connected, going out FA00, so it's going to go ahead and send that on out. And that was basically the end of that process. We've got a general breakdown of routing decisions without getting into too many specifics here on this chart. So the packet arrives on your router's interface. The router is going to search its routing table for a match. Okay, and we'll talk about how it searches for that match a little bit more in depth in a couple slides here. But basically you're seeing, does the IP address match the subnet or network of a directly connected interface? If it's a directly connected interface, it's just going to check the ARP cache, and if there's nothing in the ARP cache for that IP address, it's going to send out an ARP request if necessary, and then forward it to the host on the local network, or subnet I should say. Okay, if it's not directly connected, is it on a remote network? Okay, it's going to check for that. If it is, it's going to go ahead and encapsulate the frame and forward it out to the next hop IP address to get to the destination network if it is on a remote network. So that's what's going to happen there, encapsulating the frame, moving on out. If it's not in the ARP table at all, okay, not the ARP table, the routing table at all, no entry, no match, you've got, is there a gateway of last resort available? Gateway of last resort basically means if nothing matches, okay, if nothing matches in my routing table, then I send all other traffic out some interface, okay, which would typically head towards the internet. If there's no gateway of last resort configured, it's just going to drop the packet. If there is, then it's going to encapsulate that frame, send it on to the next hop through that gateway of last, or through the gateway of last resort to the next hop. Okay, so hopefully that's clear. That's all broken down in your readings as well. And we move on. So your best path is going to be determined by a metric. Values used to measure the distance between to a given network. And you'll see that metric show up in a readout that we see in just a moment. The best path to a network is a path with the lowest metric. Okay, and that metric can be a few different things. You have some protocols that use their own rules to build a metric. The most simple of which is going to be RIP, which is hop count. Okay, hop count basically means how many routers are in between you and the destination network. All right, that takes into account none of the speed of the links between you and a destination network, just how many hops. You could be hopping on to a network with 10 megabit per second speed, but because it's fewer hops, you're going to use it with RIP, so it's not always the greatest. Okay, you've got open shortest path first, which is a protocol that is used between all different types of devices. Cisco, Brocade, it's not exclusive to any one. Okay, so it's cost based on cumulative bandwidth from source to destination, basically based on speed. Okay, so that's going to be a bit more reliable than RIP in most cases. Then you have Enhanced Interior Gateway Routing Protocol, or EIGRP. That is Cisco proprietary. It takes into account bandwidth, delay, load, and reliability. You want to remember that those are the items involved in EIGRP, and well, how each one of these calculates their metric, because those are definitely test questions. All right, so load balancing. Load balancing means if, let's say, the metric to get to a certain destination is the same between two routes. Okay, so they're both equal speed. What your devices will do is send basically equal amounts of data on each path, so neither one's getting overloaded, and hopefully that's causing optimum speed in reaching your destination because you're balancing the load of work between both paths. So that's what load balancing is. Basically, you can see it improves network performance, and equal cost load balancing can be configured to use both dynamic routing and static routing protocols and static routes. I'm not sure if it'll come up in a test or not, but the only protocol that lets you do unequal cost load balancing is EIGRP. Administrative distance. This is basically, well, the trustworthiness of a route or the effectiveness of a route. Again, lower is better, and you can see the default numbers, administrative distances associated with your different types of routes, whether connected, static, EIGRP, OSPF, so on and so forth. These are default administrative distances. They actually can be changed. We won't be doing that just yet, but they can be. They can be changed manually. All right, and router operation. We have talked about routing tables before, and you've got directly connected and remote routes. We saw those with a C and an L entry for the directly connected. I think we only saw D for EIGRP in your routing table before. There's also an O for OSPF that you'll see. Okay, so we did use the show IP route command. Oh, by the way, routing table stored in RAM. That's probably something you want to know too. It is stored in RAM. We use the show IP route to show the routing table. We have here local routes that are added to the routing table when an interface is configured. So this when an interface is configured, you see an L entry there, your local route. We've got a directly connected interface, which we saw has a C in front of it typically. Or it does have a C in front of it, and that's added to the routing table when the interface is configured and active. Static routes are going to be configured by, well, you. That's what static means in your routes and in your IP addresses, that you manually configured it. Then you have dynamic routes that are learned automatically based on whichever protocol is being used. So if EIGRP, OSPF is implemented, you can learn your routes that way as well. And here we just have a breakdown of what each one of those letters pretty much means. O for OSPF, D for EIGRP, R for RIP, C and L we've seen before, connected and local. So there's that. Those are the ones we'll see most, at least at this point, are the L, C, R, O, and D over there. And I believe we've seen this before in CCNA 1. Not going to go over everything again. You can see how it was learned, the administrative distance and the metric to reach whichever network, what it learned it from, the elapsed time since the network was discovered, and the interface over here. So you've got the legend down there. We've gone over that before. A newly deployed router without any configured interfaces has, yes, an empty routing table. You haven't given any IP addresses, you haven't done a no shutdown on any interfaces, so your routing table is empty. When you do a show IP route, it's very sad. Then when you have a directly connected entry, you can see the network that is directly connected. Okay, for in this case, it's the 192.168.10.0 network. That's the network. And then you have the local address for your interface on that network. So on that network, my router is, okay, I was hearing something that sounded like a bee flying around in here, but I guess it's not. Anyhow, there is the address of your link that is connected to that local network. Okay, so the interface G00 is 192.168.10.1, and that's its address on the 192.168.10.0 network. All right, and well, there's more on the directly connected networks in your routing table. You've got it beginning at the gateway of last resort and just showing your directly connected routes. That's really not too important right now. All right, in IPv6, your directly connected routes again are going to have a C and an L. Same concept. C is the network, L is the actual address of your link on that network. Okay, you could see a unicast address or a link local address here. If you have a FE80, you're going to have a link local address there. All right. And then we come to static routes. All right, here we have static routes that are going to be, well, configured by you. All right. It's a path between two networks, how you get from one place to another that you just enter in yourself. The command to configure a static route is just going to be to type in from global config IP route, and then, well, the network that you're trying to reach and its subnet mask. Okay, so that's why you got network and mask there. After that, you are going, well, either use the next hop IP address or the exit interface you're going to use to get to said network. Okay, usually it's going to be a little easier just to type in the exit interface. So an example of a static route is, let me just bring this up over here and give me a second. Here we go. All right, so here's two different ways you could write in a static route. You can go IP route, this is the network you're trying to reach, and you could just use the interface as part of the entry, or you can go IP route, network you're trying to reach, and then use the next hop IP address, okay, which would be, you're in R2 here, you're trying to get to the 225, that's where you're going to get to the 11 network, that's your next hop, so you type in that number there. Again, I think it's going to be easier for me if I just have to type S000 instead of writing out a whole IP address, but up to you how you want to do things. Okay, you also have a default route that, well, if nothing matches in your routing table, you're going to use that default route. It's going to send you basically to the gateway of last resort, and we'll hope for the best as you send traffic over there. Okay, so you can see that we've got a static route set there for default static route for the gateway of last resort. That has a S in front of it whenever it's configured, and that's something that, well, you're going to want to configure pretty much all the time. Okay, so if you have no match in your routing table, you want your traffic to go somewhere. Okay, otherwise you're only communicating with networks that you've learned or are directly connected to. Okay. A couple other static route entries you've got down here. You can see how they've been typed in. This one was configured with the interface. This one was configured with the next hop IP. So you got that. All right, your default static route in IPv6. Remember, your default static route is all zeros in IPv4. IPv6, it's all zeros as well, but a colon represents all zeros in IPv6. So that's what you get here. That's your default static route's going to be going out of serial 000 there. So that's what you got there, and you can see how you configure other static route entries. Again, it's just instead of IP route, IPv6 route. You're typing in the network that you're trying to get to, then you can type in either the next hop IP or the interface. It just looks a little messier because our brains don't like IPv6 that much just yet. And then we have dynamic routing, which is automatically learning about paths to different networks. So dynamic routing is used by routers to share information about the reachability and status of remote networks. It performs network discovery and maintains routing tables. Okay. Routers have converged after they've finished exchanging information and updating their routing tables. Basically, they know about all the routes around them. So this is a pretty well simplified version of dynamic routing. Basically, R1 saying, hey, R2, I know about these networks and how you get to them. And here's that information. What do you know? R2 says, I know about the networks over here, so use me to get there. I'm your next hop, and I'm going to take the information you've given me and put it in my routing table. So you're exchanging information to build a routing table as to how to get to different networks dynamically, which is good. It has advantages over static, because if there's multiple ways to get to a network and one goes down, that dynamic routing protocol can automatically get around that and choose a new best path to a certain network. Whereas if you had a static entry, then your static path went down, nothing's going to happen. You're kind of stuck. All right, Cisco routers can support a variety of different dynamic routing protocols. You got these. If you're looking to see which protocols are supported by your Cisco router, you can type router ? and it will show you all those protocols that are supported. And we're not configuring these things yet. We will soon. Not yet. But you can see what those will look like in a routing table. You've got, again, D for EIGRP, so you'll see that there. And yeah, those are just, I don't know, entries in your routing table for dynamic routing protocols. We've got IPv6 dynamic routing protocols. You got RIP NG for next generation. OSPF V3, not V2 or V6, but V3 for IPv6. Okay, rather than just regular OSPF. And EIGRP is just EIGRP, but for V6. And if you want to know what IPv6 routing protocols are supported. You've got the IPv6 router question mark that you see here. Well, as we move along to seeing what those entries look like in your routing table, and then, you know, nothing too different. With although with the v6 you will have the link local showing up as to how you know how to get to a certain network. You use that certain link local address rather than to the global unicast. So don't let that throw you off. The link local address will pop up every now and then. And then we are done with this chapter. All right, so that's chapter 1. Few review concepts. Also throwing in a lot of routing table and static, dynamic, directly connected entries in your routing table. So a little bit of new stuff, but I'd say, I don't know, 30% review. Anyway, that's it for the video.